Welcome guys. Welcome guys. So in this video, we are trying to prove that the geodesic equation. Okay. So our setting for the geodesic equation is that right, this is the curve manifold. So there's a metric tensor Gij, and you need to solve the minimum distance from A to B, right? So by definition, your infinitesimal distance is Gij, is ds squared is dxi dxj. So written into the right. So now these Gij, di, dxi, dj are the function of t, or basically, I mean, you can view it's function of any variable, but I mean t is a we view its time is really natural, right? So that means your Gij is there's a curve gamma of t, which gamma is from unit interval mapped to this the manifold space called X. Okay, so from here, that if we derive as a Lagrangian, then Gij should be just this. So the square, just this dxi, right, dt, right, dxj, dt. Okay, so I should say, so xi, xj are the coordinates, and let's say, yeah. So this is just right, and the sort of curve just going from your dt, from your t1 to t2. So let's say you have t1. Let's say t1 0. This is 1. And the variable is basically this is as gamma of t. So gamma of t is basically the curve, what I said before. Okay, so this is the length from A to B, right? So the key point is that we need to find a minimum. So find a minimum of L. Okay, and we can derive the geodesic equation. Okay, so let's quickly before we start, let's quickly say about the Lagrangian equation, right? So the Euler Lagrange equation is that if your variable, so now your variable contains si dot, sj dot, and this Gij, right? So Gij is a function of x, right? So Gij is also a function of the variable x1, x2, up to xn, right? And you have xi dot, xj dot. Right, so you have the first derivative and the function of x. So suppose we do it by k, right? So this is the standard. This equation is our standard equation for the Euler Lagrange. Right? So we should apply this L as this one as a density and compute this and get a geodesic. Then we will see the Christoffel symbol naturally arise. Okay, so let's start. So this L, let's say, is just Ij, Gij, and I will sometimes use Einstein convention, so I will not write Ij. Okay. Okay, so let's do it. dd by dt. So what is L dot k, right? So L dot k will be two terms. One is I, right? So we will get let's say G k j x dot j, right? Because if I is k, then it will cancel. Plus is G. Now X on this J, right? So it becomes G I K X K minus the derivative respect to let's say the derivative respect to K, right? So it's basically just I ignore summation. Okay, so I get G I J. I dot k means that the differential in respect to k. So that's Gij. K is partial k Gij. So partial k means partial xk. Okay. So this one is basically G k j x double with j, right? So plus the derivative with respect to k. So this is g k, right? So there will be the first derivative term, right? So by the chain rule, right? By the chain rule, we will get g k j. Let's say we use a dummy variable l, right? Because let's say dt will be kj, right? Will be g kj dot l x dot l, right? So this is basically the chain rule. Okay, so l x dot j plus, right, plus the same thing called d over dt, right? So it's g I k l x dot l x I plus g I k x dot I, right? Minus g I j k x dot I x dot j equal to 0. One reason I want to make this video because the geodesic equation is tedious. So there are many stupid symbols that we need to figure out. Okay, so now now we can combine these two, right? So we combine these two. So notice that the gik equals to gkj, right? So gik x dot I double I, because this I is dummy, so I can change it to j. Okay, so I can make it as the 2gkj x double j plus the 3 derivative terms, right? So I can combine these 3. I can change this li to ij and change the notation. Okay, so let's do it very carefully. Let's say this is xl xj gkj l plus lxi, right? But I is dummy, so I can change I to j. So I change it to j minus this term, right? So I change ij to lj. I change ij to, so I change I to l. Right? So we will have gkj double with j, double derivative j, plus a half gkj l plus gjk l plus glj k x dot l x j equals 0. So then we might define this as wait, let's just define it later. Okay, so finally we need to I just want to eliminate this stupid term, right? So I can just times g. Let's say I need to allow cancel this k. So I cancel the inverse matrix of this k s, right? And then times it. So the first term becomes delta, right? Because k is k is defined to be the inverse. So this is sj x double dot j plus this gks, let's say here. Right, so there's nothing we can do about this term because it's just some fixed, right? X dot l x dot j equals 0. So the first term is s double s, right? Plus a half gks gkj dot l plus gjkl plus gljk x dot l x dot j. Okay, so I can define all of these terms to be our famous crystal field symbol. Basically, it should be let's say k. I just say s. That should be k, right? Lj. So KLJ is defined to be this term. So one tip to remember is that LJ will happen in the minus term, final minus term here. Okay, so finally we get our lovely s. Sorry, it should be s, right? Because k is dummy variable, so s. So it's s LJ x dot l x j equals 0. Okay, and people like to change it back, so it's very knowing that you change s to be I and change l to be you change s to be I and l to be j and the k to be and j to be k. Then you can change it to s double I dot with gamma ijk x dot j x dot k. Right, so this is the very famous geodesic equation. Okay, so yes, very happy that we never do something stupid, so we can still get the correct answer. Okay, now this equation always happen in the general relativity and the Riemannian geometry. Okay, now I will see you guys in the next videos. Hope you love this proof.